Dear distinguished guests, ladies and gentlemen, good evening in Tokyo and good afternoon in Switzerland. Thank you for joining the EPFL Virtual Space Tour in Tokyo, which launches two very special science communication projects. I would like to, excuse me, my name is Kyoko Suzuki. I am the head of the Science and Technology Office at the Embassy of Switzerland in Japan, and I'm very happy to be your moderator for the day. Before we proceed, I would like to kindly ask our online participants to kindly stay muted during the event and make sure your Zoom profile states your full name with first and last name. And if you have any difficulties at all, please don't hesitate to put them into the chat room. Thank you. So we have a full program ahead of us, so please let me start without further ado and welcome Mr. Markus Reubi, Chargé d'Affaires of the Embassy of Switzerland in Japan, and the host of this evening.
Thank you very much, Kyoko. And let me start by thanking you and the whole team of the Science and Technology Office, Michael, Jasko, Tomoya, for organizing this series of events and this evening. Dear distinguished guests, it's my great pleasure to host this EPFL Virtual Space Tour here at the Embassy of Switzerland in Japan. It's a project which is organized, or a tour which is organized jointly between the EPFL Space Center and the Science and Technology Office, Tokyo, headed by Kyoko Suzuki. This hybrid tour also marks the launch of two very interesting projects. Those of you who are here with us today physically, you have had a chance to test these two games and projects. One of them is Tranquility Base. It's a virtual escape game. And the other one is a newest edition of the virtual reality universe project, VIRUP. So for those of you who are participating online, I hope that in one or the other occasion, you'll have the chance to experience these interaction games. So this evening is about science communication, but I would like to spend also a few words on the science policy and the space policy of Switzerland. We had the head of the space office yesterday, and he explained to us that this policy, the Swiss space policy, is built on three pillars. The first one is that Switzerland focuses on the development and use of space applications to improve the quality of life of our citizens every day. Secondly, we have a long-term commitment to space exploration for the progress of innovation and of the knowledge of society overall. And thirdly, we strive to make significant scientific, technological, and industrial contributions so that Switzerland remains a competitive, reliable, and vital partner of the space community, and of course also a very important partner of many Japanese institutions active in this area. So space is a very good topic for science communication. We see this with these two tools and two projects, VIRUP and Tranquility Base. They really showcase how Switzerland is successfully promoting the communication about science. Why is this important? Because first of all, we need scientific expertise. We need it for our decision making on the individual level, on the organization level, on the country level. And we need to explain how this science functions that we use for making our decisions. But the current COVID-19 crisis also shows us that we need a lot of public acceptance and a lot of public explanation also about what science can provide and what science can do. Our countries need to continue to invest in basic science, in applied science, and we need to have a great public acceptance of that. And with all this, we can ensure that we will continue to have on a national level a very strong education, a very strong research base, and a very strong innovation-driven society. So it's really a matter of national prosperity, but not only. We also have the Sustainable Development Goals, and if we look at them in a bit more detail, we see that actually many of them are related to science and to promoting science communication. In particular, I'm not going to read it out, but I'm going to mention the 2 goals of the Science Sustainable Development Goals, which are relevant mostly, SDG 4 and SDG 9. So in light of such rising significance, the Swiss Academy of Arts and Sciences has recently published quite interesting reports on science communication in Switzerland, about what it achieves, what the results were, a true assessment for those of you who would like to look into it. It's available online, the Swiss Academies of Arts and Sciences, or if not online, if you don't find it, I'm sure the Science and Technology Office can also help you provide the right contacts. So for all these reasons, the 2 projects that we look at, the EPL projects are truly meaningful, and I'm pleased to learn more about them this evening together with you, together with the creators, Mr. Florian Cabot. He's of the Laboratory of Astrophysics at EPFL, and also Mr. Alexandre de Montelau. He's the new president of a student association called Space at Your Service. He will explain more about that. And last but not least, we will have 2 lectures again this evening of 2 distinguished professors. I'm very pleased to announce Professor Kentaro Nagamine from Osaka University joining us online, and Dr. Yves Revaz, Senior Scientist, Laboratory of Astrophysics at EPFL. I hope I pronounced all the names and all the project abbreviations correctly. And with this, I wish you a very pleasant and joyful evening. Thank you very much.
Thank you, Mr. Reubi. And now I would like to welcome from Switzerland, Ms. Emmanuelle David, Executive Manager, EPFL Space Center, eSpace, for her opening remarks.
Thank you very much for the kind introduction. It's a great pleasure for me to be here today. My name is Emmanuelle David, and I'm the Executive Manager of EPFL Space Center, eSpace, at the Swiss Institute of Technology in Lausanne. So eSpace is an interdisciplinary hub working with students, academic institutions, international space agency, and industry partners with the overall mission to promote space-related research and education at EPFL. eSpace achieves its mission through 3 key areas: education, research, and innovative development projects. We currently focus on the research initiative on sustainable space logistics, which include missions such as removal of space debris and technologies such as relative navigation and space robotics. We also work on space outreach to foster scientific communication, and today's event is a great achievement for that. And we work on a regular basis with a community of 300 students at EPFL and around 30 professors and their labs, also within the EPFL community. I would like first to give a special thanks to the Swiss Embassy in Japan and to Kyoko Suzuki and Tomoya Dunki at the Science and Technology Office for their incredible support to organize this event. It has been a very challenging year with a lot of changes of plan due to the COVID situation. And without this support, we would not have today the Virup and the Tranquility Base presented in Japan and accessible to the general public. This is such a great achievement. Congratulations. I would like also to thank the leading house, Asia, at the Swiss Institute of Technology of Zurich, which is mandated by the Switzerland State Secretariat for Education, Research and Innovation for their financial support. And finally, I would also like to give a special thanks to Vincent Derouan, our communication manager at eSpace, Alexandre de Montelau, president of the association Space at Your Service, Yves Revaz and Florian Cabot from the Laboratory of Astrophysics, who worked very hard on this project in order to make this accessible to you. So congratulations to everyone, and I wish you a very successful event at the EPFL Virtual Space Tour in Tokyo. Thank you very much.
Thank you so much. Thank you so much for your kind words. It was a wonderful collaboration, and it feels like we are reaching outer space. Now, it is my great pleasure to welcome Mr. Florian Cabot, Scientific Assistant, Laboratory of Astrophysics, LASTRO, at EPFL, who was behind the creation of the VRAP Virtual Reality Universe project. Florian?
Thank you, Kyoko. Well, hello everyone. I'm Florian Cabot, software engineer at EPFL, and I will talk to you about VRUP, the Virtual Reality Universe project. So the main goal of VRUP is to be an outreach project using VR to immerse people in the universe as best as we can. And one thing VR is really good for by using stereoscopy is to make scales intuitive. So we had a special focus on this part of the visualization. We don't want to cheat too much, so we used as little artistic views as possible because we think accuracy of the data is important to really show people where is the state of the art of astrophysics right now. And because of this choice, we think that VRUP could be a very good foundation for scientific visualization. So what are the features of VRUP? So of course, it's a visualization tool. So the first thing we can visualize with VRUP are the cosmological scales. Here you can see one of the largest survey we have of all the galaxies in the universe, which is a SDSS survey. Each yellow dot you see here is a galaxy, and you can see a few examples of them in the foreground. There are about 5 million galaxies in these pictures. Here you can see the Gaia catalog in the background, which contains all the stars you can see on this image, and also the outline of the dust distribution in the Milky Way. This is the most complete map of the Milky Way we currently have. It contains about 1.5 billion stars. We also can show simulations with VRUP. This one is the Illustris TNG simulation, one of the biggest simulations that are currently done. This is a simulation of the cosmic web. So at the intersection of each filament you can see on screen is a galaxy cluster, which are very large objects. And speaking of galaxies, we also have simulations of galaxies. And this is a simulation that Yves Revaz did of the Milky Way. And visualized with VRUP, we can have volumetric rendering to show some gas distribution that you can see in red, and some absorption by dust, which you can see at the center, which absorbs the light from the stars. We included a lot of data into VRUP, and the two biggest catalogs we have by far are the Gaia catalog and the Illustris TNG simulation. The Gaia catalog contains more than 1.5 billion stars, which accounts for about 35 gigabytes of data. And the Illustris TNG simulation contains more than 30 billion simulation particles, which is about half a terabyte of data. Of course, visualizing all this data in real time in a virtual reality environment is very challenging, because in VR you have to render 90 frames per second, and the resolution of the headsets are at least 2 times 1080p. So there is a memory consumption problem. Of course, you can't store all this memory into system memory at once. And it's a very computation intensive problem too, because GPUs can't render all this data at once. So we had to use clever tricks and algorithmics to make this possible. It was a big part of the work, of course, as you can imagine. After the cosmological scales, we can also visualize planetary systems. So this is an example of an exoplanetary system, the Proxima Centauri system, with 2 exoplanets here, Proxima Centauri B and D. VIRB contains all the exoplanets stored in the Open Exoplanet Catalog, which means there are about 4,500 exoplanets. We don't know what those planets really look like, so we developed a way to procedurally generate their appearances. Here you can see maybe a few surface features of this planet, which is from the TRAPPIST-1 system, and its atmosphere is also procedurally generated. Of course, we don't need to procedurally generate planets we know about, so this one is Mars, and you can see Phobos on the foreground also, which is one of its 2 moons. All the data from the appearance of planets comes from NASA missions that brought back some images from the planets of the solar system. And the one we know the best, of course, is the Earth. And the way you see the Earth on this picture and the moon in the background is actually the way they look like at the very time I'm speaking. Because in VIRB, you can actually put the date and time you want to have the visualization of the solar system at the date and time you want. This is possible due to the JPL Horizons tool from NASA, which contains both natural objects and artificial objects. The most famous artificial object, of course, is the International Space Station that you can see here orbiting over Tokyo in the background. It was sometime in June this year. And we have a lot of space probes, and one of them is the Rosetta probe, which orbited the Churyumov comet back in 2013. There are a lot of ways to interact with VIRB. The main one is to free run across all the scales without apparent loading times using keyboard or VR controllers. But the universe is big and it can be overwhelming for people to navigate. So to have smoother public presentations, we use a predefined path across the universe, as you probably saw if you did the experience already. We collaborate with the Laboratory for Experimental Meteorology at EPFL, which has a lot of interesting hardware for visualization. And 3 of those installations are shown here, on which we ported VIRB. At the top left, you can see their dome. At the top right, you can see their half cave. So it's basically 2 screens, one for the floor and one for the wall, which are stereoscopic. And the panorama at the bottom, which is also stereoscopic, and it's a large 360 degrees screen. The last way to interact with VIRB is to pre-render movies with it. We released a 4-minute movie last year for the EBOS press release. And last month, we released a 20-minute movie in the Shinra Dome of the Science Museum of Tokyo that you can still see today. And this movie will be published on YouTube in October. So if you want to see it before October, you can go to the Science Museum of Tokyo to see it there. We have many future plans for VIRB, and the main one we will focus on next year will be the cosmological simulation dynamics in real-time VR. As you maybe already saw or will see in the movie, we already have all the data available, but rendering it in a movie is easy. You just have to wait for a few hours. in real time, you don't have a few hours, so it's a great challenge to show all these terabytes of data streaming in real time in a virtual reality headset. In conclusion, I'd say that with VRIP, we developed a very powerful visualization tool for all kinds of astrophysical data. And as we focused on the scientific part of the visualization, even if it's designed for outreach, we think it has basic technology for scientific visualization. So we hope to develop this aspect sometime soon. So you can get in touch with me, and please go to the VRIP website where you can download VRIP. You can also watch our movies on the Lastro EPFL channel, YouTube channel. And if you already, if you haven't already, please try the live VR demo, as it's really the best way to experience VRIP, I think. Thank you very much.
Thank you, Florian. I have also experienced the VR goggles version today. They were amazing. And I have also seen a longer version, theater version, which is also more explanatory and it explains to us more in depth what this project can convey. So I would really recommend those who have not yet seen these projects to experience, hopefully in the fully immersive mode, but if not, also the longer version is very impressive. Thank you very much, Florian. Now I would like to move on to Mr. Alexandre de Montelau, the new president of Space at Your Service, EPFL. Alexandre?
Thank you so much, Kyoko. There we go. So good morning, everybody from Switzerland. Good evening, everybody from Japan. I'm so honored and proud to take part at the EPFL Virtual Space Tour. So my name is Alexandre de Montelau. I am a EPFL master student in robotics and also president of Space at Your Service. This event, the EPFL Virtual Space Tour, is very important for me because it also means the launch of a project my association and I have been working on for almost a year now, which is Tranquility Base, that I will present to you today. But before that, let me explain to you quickly what is Space at Your Service. So we are an EPFL recognized association. We are specialized in the promotion of space sciences in multiple ways to the general public and the students community. For projects and events, we work a lot in collaboration with different entities such as the EPFL Space Center, laboratories, and also government institutions, for example, for Tranquility Base. I'm also going to give you a quick overview of what we do at our association. So we are pretty known on the campus for doing what we call astronomy on tap, that you can see on the left pictures. The concept is the following. They are informal conferences where professionals from the space field go on stage and talk about what he does, what he did. Everything takes place in a bar, and the concept is that everybody has got a beer. It's more informal at a conference, and after there is a long discussion between the public and the speaker. Maybe some of you have recognized him, but you can see on the top left picture Claude Nicolier, who is a former Swiss astronaut. He went to multiple at our events, and he will come back in the future. We also do a lot of workshops in schools. You can see that on the top right pictures. We call it Vivalis Mission. And last but not least, and this is what I will present to you today, Tranquility Base, the last project, biggest project of our association last year. Before presenting Tranquility Base, I think it's important to say this, that this project is multidisciplinary, which means that people from very different worlds were connected thanks to this project. So we have laboratories, space-related entities, government institution, video game studio, and we were coordinated all this work in the aim to create Tranquility Base. So what is Tranquility Base? Well, it is an augmented reality multiplayer smartphone escape game on the theme of space. It sounds very specific, but the principle is pretty simple. If you watch the left picture, you can see someone playing the game. So it is a smartphone game. You can have a tablet or a smartphone. And it is augmented reality, which means that you scan the ground using the tracking system of the camera of your device. And after a virtual world appears to you, it is a two-player game that takes place in two different spaces. We have a lunar base that you can see on the top right picture, and a mission control center that you can see on the bottom right picture. So it is a two-player game, as I said. One person is in the lunar base, the other one is in the mission control center. And the scenario is the following. So you have a lunar earthquake that has hardly damaged the lunar base. The oxygen is dropping down, and you have 20 minutes with your teammate who is in the other room to collaborate with him and find a solution to save the mission. Tranquility Base is very special. So why we did this game? First of all, let me talk about why this game is unique. So it is a science communication tool never seen before in the world for, I would say, 3 reasons. The first one, I've said it, it is because it is a multiplayer augmented reality escape game on smartphone. Also, and I will come back to that later, because it contains current Swiss space research projects that are virtually present in the game, and the scenario is based on real science. The purpose of Tranquility Base, and this is why we did this game, is to show through research projects that are virtually present in the game what a lunar base can look like in 2050. We also want to promote Swiss contributions to the space field. All research projects that are in the game are from Swiss laboratories. And we want to show in this way that Switzerland is a really strong space nation. And also, of course, give people knowledge about space. So let me move on to research projects that are present in the game from now. To make the long story short, so we reached 4 laboratories and asked them if we could put a virtual version of the device they are developing into our game and giving them an application. So the first project that is in our game are modular origami robots called Mori from the Reconfigurable Robotic Lab at EPFL. These robots are they are triangle shapes that can fit together in the aim to create complex structures. And the application we gave to Mori, and you can see that on the right picture, top right, is that Mori are actually the shell of the lunar base. And on the bottom picture, you can see an isolated picture of a virtual version of Mori. The other project that is present in the game is Amisru from Thermomechanical Meteorology Laboratory at EPFL as well. What they do is they, using additive manufacturing processes, they extract the rocks, the regolith, lunar regolith. So it's a rock that is present at the surface of the moon. And with this rock, what they do is that they extract the oxygen. And the application we gave to Amisru is, of course, that Amisru is the oxygen supply of the lunar base. And last but not least, we have Spacebug from the Robotic System Lab at ETH Zurich. It is a crazy robot. And the goal is the following. This robot is made to go to regions that have never been reached by robots because it was too difficult for them. So Spacebook is supposed to go everywhere on the moon, and the application we gave to him is that Spacebook is the explorative robot of the lunar base. So some of you have already tried the game, some of you not, but I will talk about as well hidden elements. We have a lot of hidden elements in the game. This is also another way to communicate on space sciences. And I will show it through 3 examples that I will present. So I will reveal some hidden elements, but don't worry, there are a lot more. And I encourage you that when you will try or retry the game to refine these hidden elements and try to find the new ones. So for example, on the left picture, we can see good luck peanuts that are present at every NASA's launch. Also on the middle picture, you can see a little Swiss cube. So Swiss cube was a Swiss satellite that was developed by, I think it was around 250 students from EPFL and was launched in 2009 to space. And on the right side, believe it or not, but you can see a lightsaber because back in the 90s, an astronaut took a lightsaber from Star Wars movie and brought it to space. What is the future of the game? Well, this game is made to evolve in the future. This is, we want to have, of course, more puzzles, but more than ever, more research projects in it. We want this game to getting bigger in the future and travel the world at many events. From now, our game will be present at the Dubai World Expo in October 2021. The game is already available on App Store and Play Store, so please go and try the game. You can play at home, tap Tranquility Base, and you can play this game. If you want to know more about Tranquility Base, please, I encourage you to go to the websites. There's everything I talked to you about and also some more information. And if you have any questions, I would be more than happy to answer them. So don't hesitate to contact me directly. And last but not least, this project started from an idea a year ago, and now we can see that it is real. And this project goes beyond what we expected at the beginning in terms of quality, in terms of content. So I would like to, of course, have a special thanks to all of sponsors who always believed in us and keep supporting us. So thank you so much.
Thank you very much, Alexandre. And now to our keynote speakers that will inform us of our galaxy, the Milky Way, in a cosmological context, excuse me. I would like to first welcome Professor Kentaro Nagamine from the Graduate School of Science, Department of Earth and Space Science at Osaka University. Professor Nagamine, please.
Thank you very much for the introduction. I'm Ken Nagamine from Osaka University, and it's a pleasure to be here today. And let us present what we do in our research field. Together with Professor Yves Revaz, we'd like to tell you a little bit about our galaxy, the Milky Way, in a cosmological context. And in this first page, I'm trying to depict that what we try to do is to start from the initial conditions that we observe in the cosmic microwave background radiation. Then we'd like to reproduce the formation and evolution of the large-scale structure, and eventually the galaxy formation and star, planet, life formation eventually on Earth. I only have 10 slides, so it's going to be a quick 10-minute presentation, and then I will hand the mic to Professor Revaz to talk more details about the galaxy formation. Let me start by this brief history of structure formation in the Big Bang universe. From various astronomical and theoretical studies, we now believe that the universe started in an event called Big Bang, the beginning of the space-time. And then there the quantum fluctuations were imprinted on this that we see in the cosmic microwave background radiation that we witness at the cosmic age of 380,000 years after the Big Bang. there was a brief period of dark age where nothing really happened until through the gravitational instability of dark matter, the first objects, such as the first stars or the first galaxies, started to forming around several 100 million years ago after the Big Bang. And then after that, there was a long period of development of galaxies and planets. And then we now, I believe that we live in the world of 13.8 billion years after the Big Bang. Another interesting aspect I will touch on later is that we think that the universe is accelerating in its expansion due to energy component called dark energy, which seems to lie in the vacuum of our space. So that's our standard theory of structure formation. And that is based on this holy grail of astronomical observation called the cosmic microwave background radiation. And that was discovered by these two gentlemen called Penzias and Wilson in 1965. And they have detected the radiation left over from the fireball of the Big Bang with this radio telescope in the background. And they were given the Nobel Prize in Physics in 1978 due to their contribution of this discovery. Interesting story that goes with this is that there was another paper, theoretical paper, that was published at the same time by Dickey and Peebles, who gave theoretical interpretations of this cosmic microwave background radiation. And I will touch on that later too. So here's an observed image of the temperature fluctuations of the Cmbr. We call it Cmbr. And after subtracting off the average intensity of this radiation that comes from the entire sky in the wavelength of the radio wavelength, you will see this fluctuation that is in 1 part per 100,000, which is 10 to the minus 5, as you see on the pictures on the left. The top image is from the Reubi satellite that was acquired in this time period. It's the first satellite that acquired this data. And they also got a Nobel Prize. The PI of this project called John Mather got the Nobel Prize. And then another project called WMAP, Wilkinson Microwave Anisotropy Probe, also collected data and acquired this higher resolution data during this decade from 2001 to 2010. And then also the European effort, the Planck satellite. This is the image from ESA in March 2013. Already close to 10 years ago, but this is still hot and new for us. It also acquired this high resolution image of this CMB. And all of these satellites show that it's a black body radiation about 3 Kelvin with this tiny fluctuations imprinted, which we believe that it comes from quantum fluctuations in the early universe. The big picture hasn't changed very much from the early data. And as I said earlier, another Nobel Prize winner of 2019 was Professor James Peebles from Princeton, and for contributions to understanding of the evolution of the universe and Earth's place in the cosmos, which is exactly the theme that we're discussing today. And he contributed significantly to the theoretical discoveries of physical cosmology, such as the Cmbr anisotropy that I just showed, and also on the topic of dark matter, dark energy, and galaxy formation as a probe of dark matter, which Yves will later discuss further. And the two gentlemen on the right have got the part of the prize at the same year for the discovery of the exoplanets, which is another very hot topic in recent years in the astronomical field. And we have already a few thousands of candidates of extrasolar planets around the system. Here's a short movie from NASA, which shows how we measure the geometry of space-time from Cmbr anisotropy. From theoretical calculations, we actually know how large the physical size of these patches are, which are the hot red region and the cold blue region. And by comparing that size to the actual observed apparent size of these patches, the anisotropy, we can measure how the light ray actually propagate through the space. If the space is flat, the two light rays will propagate parallel to each other. But if the universe is closed, for example, the two laser beams will actually start to converge as they travel through the space. And vice versa, if the space is open with negative curvature, then the two laser beams will start to diverge with each other as they travel through space. And so this is how we measure the geometry of the space-time. And not just from the CMB, but from other observations as well. By combining all of those data, we infer that the energy of a universe is dominated by dark energy, which occupies about 74% based on the best fit model. And the dark matter density, including dark matter and normal matter, is only 26% of the total, as you see in this pie chart. And then out of that 26%, about 22% is dark matter, and only 4% are the regular atoms that we know of, like gas, stars. And in terms of elements, the elements like hydrogen, helium, carbon, nitrogen, oxygen, all those atoms that we know of on Earth only falls into this small portion of this pie chart. So there is a very small portion of energy density in our universe. And the large part of our universe is still unknown energy components. And that is a mystery that we still try to solve in the modern cosmological studies. The total energy is very close to the critical density of the universe, which allows the universe to barely expand until a certain point. And then because of this dark energy effect, the universe started to accelerate in its expansion at a later time. So it's a very strange universe dominated by dark energy and dark matter. Okay, so here's a image that depicts how we actually know these things. Another data that supports this acceleration, the dark energy, it comes from this data of the supernova observation. We observe a very distant type 1a supernova, which tells us how the universe has been expanding over the past. So this plot shows on the y-axis the average distances between the galaxies. In other words, it's the expansion rate of the universe. And on the right, you see the cosmic time, normalized at the present day over here. So these data lies on top of this particular line that suggests the existence of significant amount of dark energy. And other models actually fail to describe these data of the distant supernova. So this discovery of dark energy also resulted in 2011 Nobel Prize in Physics to these three gentlemen for the discovery of the accelerating expansion of the universe through observations of distant supernovae. So you'll see that the past several decades in cosmology, there has been significant advancement and also recognition from the community. Let me just show one example of a Japanese effort to understand the structure formation. The previous speaker, Florian, I think I explained about the luster simulations, and this is a similar, very large cosmological n-body simulation showing the matter distribution, projected matter distribution. The largest scale is billions of light years, and that is almost very close to the observable universe. And then this tick mark over here is 100 million light years across. And in the central part, you see a very large supercluster. And as you zoom in, you go into 50 million light years, 10 million light years. And this is one galaxy cluster over here, which contains thousands of galaxies. And each of these little light dots contain a galaxy. And if you were to run a simulation with the baryons, with the regular gas, as Dr. Revaz will talk next, we'll see the galaxies form within these dark matter halos. Let me end by showing this movie of this evolution of this matter density field in that particular simulation. The universe started from almost uniform, but with slight fluctuations, as I explained earlier. That was imprinted in the quantum fluctuations in the early universe. And then through gravitational instability, those dark matter start to pull together, and then they coagulate, and then they start to form these so-called dark matter halos, which is a collection of billions of particles of dark matter particles. And then once these dark matter halos form in the cosmic web, then the gas will eventually cool further down to smaller scales, and then the formation of the first stars and the first galaxy will continue furthermore. Okay, so that is how we think this evolution of a structure formation occurred in this universe, starting from the Big Bang and to the present day of 13.8 billion years later on. And we have a good understanding and sense of what has happened on global scale like this, but in details, there's still a lot of unknown questions unanswered remaining in this. That's what the next lecture will be. So thank you very much, and we can take more questions later, and I will pass the mic back to the MC, please. Thank you.
Thank you very much, Professor Nagamine, for the interesting presentation and the beautiful images. So I would like to continue to ask Dr. Yves Revaz, Laboratory of Astrophysics at EPFL, to continue with his presentation. And I would like to also say that he is the primary investigator of the VIRUP project as well. Yves, the stage is yours.
Yes, thank you, Kyoko. Can you, oh, I need to share my screen. Yes. Can you see the slide?
Yes.
Good. So thank you, Kyoko, for the introduction, and thank you, Professor Nagamine, for the very nice introduction you did. That will be very helpful for my own talk. So in this short presentation, what I would like to explain you is how we can now simulate the formation and evolution of Milky Way-like galaxy out of a cosmological context. In fact, I will take the opportunity during this talk to also demonstrate you that to understand formation of galaxies, it's very important to build strong teams, strong interventional teams. And I wanted to stress that both Professor Nagamine and me are part of this kind of teams. Good. So let me now remind you what is one of the major goals that astrophysicists want to reach. It's nothing else than trying to understand if and how a galaxy like our own Milky Way can form from a nearly homogeneous universe, so exactly the kind of universe that are predicted by the standard models of cosmology, like Professor Nagamine explained you. So in fact, we know, thanks to the cosmic microwave background measurement, we know that something like about 400,000 years after the Big Bang, the universe was nearly homogeneous, but only imprinted by very tiny fluctuations that are shown here in the picture that Professor Nagamine already showed us. The question now is, how is it possible from this tiny fluctuation to generate a Milky Way-like galaxy like the one which you can show here? I wanted just to precise that this picture is not a real galaxy. In fact, it's an artistic view of our galaxy, because of course, as living inside our galaxy, it's not possible to have a nice and entire view of our own galaxy. So the question is how we move from this universe to that one. And I want to convince you that doing so, understanding how things proceed, is extremely challenging for three main reasons. The first one is that it's very strongly nonlinear problem. The second one, it is a multi-scale problem. And the third one is a multi-physics problem. Let me concentrate on what we call a strongly nonlinear problem. In fact, imagine that you start from the very early universe. The universe is nearly homogeneous, except that in some region you have a portion of the universe that are slightly denser. This is what we have sketched here. You see that you have region like this one here, which is slightly denser than other regions. Now, it means that if you look at the gravity forces, you know that gravity forces due to the accumulation of matter here will attract the surrounding regions. So what this will make is that you will attract more mass, and you will make this region, which was originally slightly denser, even denser. And if it becomes denser, of course, the gravitational forces will increase, and you will be able to attract more matter from the surrounding regions, and you end up with making this initial portion even denser. So the more you attract surrounding matter, the more we attract it. Okay, so this is exactly what we call a nonlinear problem. The second challenge is that you have to deal with a multi-scale problem. As Professor Nagamine explained you, we need to start by focusing on very large portion of the universe, typically the size of 1 billion light years across. And at the end of the day, we want to understand objects that are 4 orders of magnitude smaller. So typical galaxy has a size of something like 100,000 light years. So it means that you need to solve a problem over 4 orders of magnitude. But this is not everything. In fact, if you want to really understand in detail how a galaxy evolves, you need to solve what is at the origin of its stars, and typically large regions of gas that we call molecular clouds. And these regions are much smaller. You can see some of them here corresponding to the pink patches. And there is a zoom of one of these clouds observed in the sky, the Horizon Nebula, which is only 100 light years across. And if you want to follow the formation of the stars, you even need to go further by studying how protostars forms, and that object that have only a size of 10 light years. So you see that in total, you will have to span 8 orders of magnitude in space. So that's a very challenging problem. And finally, I wanted to mention that it is also understanding the formation of galaxies is also a multi-physics problem. In fact, we all know that what drives the formation of galaxies is gravity, which is slightly less known is that gas also play a major role. So we have not only to understand how gravity works at large scale, but we also need to understand the evolution of gas through hydrodynamic equations. Now the gas is something which is a bit complex. We know that gas may cool down, it may lose energy by radiating photons, but it can also be heated. And that's important to take into account when we want to understand the galaxy formation, because as Professor Nagamine mentioned, this is really the core, the core of the formation of galaxy. You have gas that lose energy and may collapse and then form stars. So we need to understand how it works. Of course, we need to understand how it's possible to turn gas into stars. That's something which is quite complex. I wanted also to mention that once you have formed stars, something which is now known since many years is that stars will have a very important impact on the gas that didn't form stars yet. So what is called the stellar feedback, the most massive stars will very quickly explode as supernova, and they will release a large quantity of energy that will be able to self-regulate the star formation in galaxies. There are many other processes that I could explain you here. I can very quickly mention, for example, that sometimes it's important to take into account cosmic rays or dust. We can also include magnetic field that will regulate also the star formation and so on and so forth. But the main message I wanted to give you here is that it's a really complex multi-physics problem. So putting all together these 3 challenges, you see that in order to understand the formation of galaxies in a cosmological context, there is no way to rely only on mathematics. I mean, you cannot just play with pure analytical mathematics and solve anything. So what we need to do here is really to use simulation, to develop complex numerical models that will, thanks to computers, that will simulate the formation of galaxies. And since now about 50 years, there have been a lot of progresses to develop different methods that allow us now to understand the formation of galaxies. This is certainly my most busy and tricky plot, but I wanted to very briefly mention that we now have different competing methods that have been developed to, for example, follow or to solve the hydrodynamics in the universe. And I wanted to quickly mention 4 of them. There is one where the gas is simply, or the matter in general is represented by particles. There is a very nice method called the smooth particle hydrodynamic method, which helps you to solve the hydrodynamical equations by simply computing thermodynamical quantities on individual particles by the convolution over many particles. And that's a very nice way of simulating a continuous system like the gas is. A more common method is the so-called adaptive mesh refinement method, which rely on a grid, on an Eulerian grid, that's on which we solve the hydrodynamical equations, but it is supplemented by a refinement technique. I told you that we are dealing with multi-scale problems, so you can use this method to have a very coarse resolution in regions where we have few matter, but increase strongly the resolution in region where you have a lot of matter. And this is the way you can solve these multi-scale problems. We have seen now since something like 10 years, the apparition of a very nice method, which is an hybrid method between the SPH and the Cmbr method, where you sample space with particles, that the red dot here, but you use more accurate hydrodynamical solver by defining cells around your particles, which correspond to, technically speaking, Voronoi tessellations. And the funny thing with this method is that if you let the system evolve, you will see the red particles evolving, but you will also see the shells, the cells around those particles that move continuously. This is why it's called the moving mesh method. And finally, since 5 years, we've seen the apparition on another method, which is quite similar to the previous one, but has the advantage of avoiding to explicitly define the grid here. That's it relies simply on a very smart mathematical trick. So we are left now with different methods, and one of the challenge is to understand, well, to try to know which one of these different methods works the best, which one we should maybe all use. In order to do that, it's very important to compare these different methods. And this is why with Professor Nagamine, we are both participating to the so-called Agora high-resolution galaxy simulation comparison project, which is a project designed to understand, well, to compare codes that are able to form galaxies out of cosmological context. The idea is that we all simulate the same volume of the universe, we all use the same initial conditions, and we are sharing also some common physics, like, for example, we all choose the same way of cooling the gas, of heating it, or to form stars. But we are all using different codes, and then, of course, different hydro and gravity solvers. Okay, those last years we have played with two different, well, we have performed two different tests. The first one was the so-called isolated disk test, where in fact every team had to simulate a galaxy in isolation, starting from very simple initial condition that you can see here. 9 codes participated to this project, and you see the initial condition they used. So it was a flattened disk, so a typical spiral galaxy without initially the spirals. You see the disk edge on here, and you see the disk face on. And in order to illustrate more what the simulation looks like, let me show you a movie we have realized with our own code gear. So you can see that starting from the initial conditions, so you very quickly see the formation of complex spiral structures that are permanently formed and destroyed. We see here, we see here the pink patches that correspond to the region where very young stars have been formed. And you see also, thanks to dust treatments, dust lanes that correspond to absorptions of light. So we are able to very nicely reproduce features of Milky Way-like galaxies. Let me see you the same simulations, but seen from different point of view. In blue here, you see the gas. In the yellowish colors, you see the stars. And what I wanted to show you through this video is the complexity of the interstellar medium, so the gas in blue that is permanently heated by the exploding stars, generating a lot of turbulences. You see sometimes very well the explosion that pushes the gas away and generate these turbulences. Okay. See also how these spiral structures are developed thanks to the interplay between gravity and rotation. Okay, so having all run these isolated disks, we have been able to compare the results of the different codes after 500 mega-year of evolution, and this is the result we obtained. So I won't go into more detail. I just wanted to show you that we all have been able to reproduce in a pretty similar way the spiral structures that you can see here. And I wanted to stress that this model here is called here Gadget 3, is the Japanese, has been run by the Japanese group, and this is the Swiss team with the gear code. And you see that we end up with a very, very similar results. Now, the second test we've performed recently, well, recently it was work done during the last 3 years, is to simulate the cosmological box and see how we can generate a galaxy like Milky Way-like galaxy out of it. So we're starting from a box which has a size of about 180 mega light year. We use a zoom-in technique, which consists in adding very high resolution only in a tiny portion of the box where we know that the Milky Way-like galaxy will form. Let me directly show you the evolution of this simulation. I compare here the evolution of two models, one which has been run with the Ramses model and one with the Kia. And you see here in orange, the unseen matter, what is called the dark matter. You see that in both cases, we predict the formation of the galaxy by the fusion of different pieces, well, smaller blobs of dark matter that merge all together to form, at the end of the day, a very massive halo. Let me maybe run this movie another time. Of course, in these simulations, you can very easily understand that if you look at in details, you see different features. You have more substructure here, for example, but the important message to get is that in average, we manage to have nice converging results. We'll show you another movie that now, instead of showing you the dark matter, shows the evolution of the gas. Here again, you see a nice agreement between the two. Of course, details are slightly different. You see that we all form a first filamentary structure that then fragment to form, to give birth to the galaxy that is building here by accreting different small pieces. Okay, so wanted to show you this last slide. That's compare at the end of the day the galaxy that have been formed out of these cosmological simulations. You see here on the top line the mass distribution, the gas mass distribution. You see that the mass distribution is pretty similar among the 7 codes that have been involved in this study. You have on the bottom the stars as they have predicted. Again, you see differences, but in average, the quantity of stars that have been reproduced is in agreement. And you have the gas, the temperature of the gas, and it's interesting to see here that we have differences. For example, the grid base code, that these three codes, does not reproduce the hot gas, which is reproduced by the particle base code. You see once again that the Japanese group and the Swiss group have pretty similar predictions. So let me quickly conclude. I hope I did convince you that forming a Milky Way-like galaxy in a cosmological context is extremely challenging because we are facing a nonlinear problem, a multi-physics problem, and a multi-scale problem. In order to simulate this kind of galaxies out of cosmological context, we usually need large international collaboration in which both Japan and Switzerland participate. We've seen through this kind of collaboration that very good agreements are found when using different code. However, there are still some discrepancies. And I wanted to conclude by simply saying that I have been very happy to see that both Japanese and Swiss predictions agree quite well with each other. And I will stop here.
Thank you very much, Yves, and also for the nice conclusion. The presentation was extremely interesting, and the scale was overwhelming and amazing. So thank you very much. Now I would like to invite questions from the audience. And also, since the magnitude of the presentations are quite huge, if someone would like to share their impression of what has been shared with us, this is also welcome. And for our online participants, if you would like to make a statement or give your impression or ask a question, please raise your hand in the Zoom function, which is found at the bottom of your Zoom window under the button reaction. Or as you see in the chat, you may also ask or state your comment in the chat box if you like. So may I invite any questions or comments from the audience? Sorry? Yes, please. If you do not mind stepping up to the podium so people can see you as well. Thank you.
Okay, so hello. So I'm Xavier Defago of Tokyo Tech. It is absolutely not my field, so I'm going to ask a very naive question. In your simulation, so well, you show how the formation of the galaxies, but actually the galaxies are spinning, and I mean, as far as I know. And I would like to know what is the reason why they would start spinning. So is there any explanation? So I don't believe it's due to Coriolis acceleration. So I would like to maybe if you can just bring some light on that.
So I don't know. Well, I'm pretty sure that Professor Nagamine can also answer the question. I don't know if you want to answer, or I can.
Yeah, the standard theory is actually from Professor Peebles, which I showed in my slide, and he proposed that the tidal interaction of the matter with the galaxy and also the nearby galaxy, as they form and as they condense, they have gravitational interaction with each other. So through those the interaction, they actually move around and then they exchange angular momentum, and that's actually tried to an isotropic non-uniform matter distribution around the galaxy actually pulls the matter, and then gradually as the matter collapses, it appears that it rotates much faster and faster as they reduce its scale. Yeah, so that's the standard theory. It's a tidal interaction with an ambient medium.
So yeah, thank you very much.
This is, if I may add, this is a really nice feature you can see when you look at the simulation. So thanks to movie we can perform, or now looking at the evolution in a virtual reality environment, you see very nicely how these blobs are accreted and how by keeping the angular momentum, everything really starts rotating.
Thank you very much. It was just a pure curiosity, and thank you very much for the.
Thank you very much for the question. Would someone else like to make a statement or a comment, question? If not, I also had two very naive questions, or somewhat out of the range questions. The first one, I was hoping to get the impressions of Professor Nagamine and Dr. Revaz, and perhaps also Florian, on the future of simulation and the role that artificial intelligence might play. If you have any dreams or concrete outlooks. So that would be question number one.
Okay, I can start by answering that astronomers are beginning to utilize AI quite a lot these days. And I was actually attending the Japanese Astronomical Society meeting over the past few days. And the younger people are more and more attracted towards such research, utilizing AI and deep learning techniques to analyze the large cosmological data sets, which Florian also discussed. And it's very helpful to extract certain correlations and important visual aspects that the human simply cannot digest and extract because of its sheer size. And so it's beginning to be a core tool of our research, and in the near future, I think it'll expand more and more. Yeah, please go ahead and add more.
So I fully agree with Kentaro, sorry. AI becomes extremely important in the field of astrophysics, but as Kentaro precisely said, it is mainly used to analyze outputs of either large simulations or large data sets. I think it's important to stress that I'm still believe in theoretical works, and I will try to explain you my point of view. The question could be, would artificial intelligence have helped us in understanding, for example, general relativity or quantum physics? And the message I wanted to tell you is that AI may do a lot. It will help in the analysis, but we still need the human brain to progress in some field in physics.
Thank you very much. Florian, would you like to also add something?
Well, actually, I don't participate in the simulations. I only do the visualizations, but also in visualization, artificial intelligence is more and more used. So it's actually any field that uses a computer is no subject to being enhanced by AI those days. So yes, I'm sure astrophysics can benefit from it too.
Thank you very much. And the second question I actually had is also maybe a little bit silly, but the filament structure at the very end of Professor Nagamine showed the very beautiful cosmic web, which I learned through Europe that it is called cosmic web. To me, it looks like a very organic structure as well that we might see in a plant or something on Earth. So I was wondering if there are some commonalities or things that are talked about in the field of science that is interdisciplinary.
Yeah, that's an interesting question. It does look like a neural network, for example. But in the case of the structure is gravity, and in terms of physics, it probably is. Maybe there was a little bit of an intermission. Yeah, yeah. Well, in the case of biology, it's not gravity that produces those structures. So the particular interactions that produces on neural network, for example. There could be some similar scalability in that's appearing to produce.
I'm sorry, but I think you have been a bit cut, so I didn't get the all you answer. I think I got the point, and I fully agree with that. I wanted to mention so that it is far from the first time that people see this analogy between a complex network of cells, for example, that could be cells, neurons, and the large-scale structure of the universe. And I remember some years ago we were competing, well, not competing, but we were showing 3D movies of the formation of the universe. And in parallel, there was a very important group at EPFL, the Blue Brain project, that are working on understanding the neurons, and they were showing nearly similar picture. There was, of course, lots of people that were asking, how can we compare that? And as Kentaro answered, if I got all the answer, I mean, in the case of the universe, of course, that's gravity that dominates. So while at the level of neurons, that's van der Waals force or intermolecular forces, so that's quite different.
Thank you very much. I feel a little bit embarrassed that I should have known that this is the outcome of gravity, because I have seen the Virop movie, the longer version, and it tells me that it is the result of gravity. So there is no, the difference is very clear. But I feel this kind of these kinds of presentations, if I had learned about them, for example, at a very younger age, could have gotten me very much interested at an earlier time into these very meaningful and important topics for our times. So I hope that we have more of these presentations also to a broader audience. And I think this was a very fascinating presentations for me. Thank you very much. And also for the audience, I believe. So if there are no more questions, I would like to say thank you to all our speakers today, and also to add to our sponsors and collaborators, the EPFL and EPFL eSpace, EPFL Space Center eSpace, the Leading House Asia, which is also working together with our headquarters, State Secretariat for Education, Research and Innovation, which also is the host of the SwissNext network, which the Science and Technology Office Tokyo is also a part of. We were also very much supported by Présence Suisse and the Swiss Tech campaign. So thank you very much to them. And I would also like to take this opportunity to thank two individuals who are not on the screen today, but or who have been very critical in realizing this project. The first one being my team member, Michael Vogelsanger, who worked behind the scenes, and also the previous president and founder of Space at Your Service, Chloe Carrier, who may know as Galaxy Chloe, I believe. So I would like to thank everyone again and wish you a nice afternoon and a nice evening. Thank you very much.